this video, we will generalize what we've learned for single ordinary differential equations to systems of first order ordinary differential equations. Now, systems of first order differential equations, well, they occur whenever you have several dependent variables which have interactions amongst each other and then lead to coupled equations. For example, when looking at some chemical kinetics reactions, and this is an example we also looked at in the initial video for this chapter, we see that we have, let's say, three different variables over here. So the concentration of NO, the concentration of Br2, and the concentration of NOBr. And well, based on this chemical reaction with constants K1 and K2, you can write down these three equations which are coupled. So you see that the concentration of NO depends on the concentration of NO, but also on the concentration of NOBr and of Br2. And the same holds for the other constituents of this equation. Now, in order to solve these, well, we have to be able to solve them all together because you cannot solve them one by one since they are coupled. Another example is here a predator-prey system. And these equations are named the Lotka-Volterra equations for reference. And in predator-prey systems, well, the amount of predators and the amount of preys, they also interact. So if there are very many prey available, then also the predators will start to increase in number because they have ample food. But then the amount of prey will obviously decline as more and more predators start eating more of the prey, which also has an inverse feedback effect on the amount of predators. So this is also a complex and non-linear coupling between the amount of predators X and the amount of prey Y that you have in the amount of predators is actually Y and the amount of prey is X that you have in a certain population. And this is a highly nonlinear coupled system as well. Now, in order to solve such systems of first order differential equations, well, that's basically a quite natural extension to solving single ordinary differential equations. And here in the notation, I just consider the independent variable to be the time, t. So instead of x, I use t here. But that's let's say more of a detail. But what we find is that, well, let's say that we have n coupled equations. So we have n functions that we want to find, y1, y2, up until yn, which are governed by these functions f1, f2, and fn, where every function can be dependent on both time, but also all the other unknown functions over here. And we also have to supply initial conditions for each and every function of this system. But we can rewrite this a bit more compactly into this notation over here, where I use boldface for vectors. So if we define the vector y as having components y1, y2, up until yn, we define the vector f as having components f1, f2, and until fn, then we can easily rewrite this system of equations into a more compact form where this is a system of equations with these vectors y, f, and also y naught, which holds all the initial conditions. Now, solving such a system of first order equations, so again, recall that y, f, and y naught over here are vectors. It's rather straightforward, and there's not really much that you have to change to your methods in order to be able to cope with systems, as this is all really quite a natural extension if you work things out component-wise. So for example, looking at explicit Euler, so here we have time as an independent variable, so we partition the time axis instead of the x-axis as before, so that's straightforward. But then our explicit Euler formula is that, well, based on the current vector solution, so this holds all these functions or all these numerical values, the function y1 at time step I, the function y2 at time step I, the function yn at time step I, that is this vector over here, plus h times the vector f evaluated at ti and yi. So component-wise, that looks like this. That results then in the component-wise solution at the next time step according to this. So you can simply apply the methods that we've used so far component-wise, and in MATLAB that is almost trivial to do. You can apply them component-wise, and for the rest, nothing much has to change when looking at systems versus single equations. For example, also modified Euler can be used, where then this intermediate solution y star is now also not a scalar variable or a scalar number, but it's a vector of values, and we simply also just compute two different kinds of slopes where each of these bold-faced f's holds n slopes. We average them out and use them to update the solution. So to be fair, nothing much changes when you, at least from a algorithmic point of view, nothing much changes when looking at systems of first order differential equations. So let's look at an example to make this a bit more clear. And let's look at a very actual example where we try to model the outbreak of an epidemic using a so-called SIR model. An SIR model, well, that divides the population into three groups. A group of susceptible people, a group of infected people, and a group of recovered people. And we don't consider here the fact that the disease might be fatal, so everyone that's infected becomes a recovered person. So these different groups, well, they interact through two processes. Well, there is the transition of people from susceptible to infected through infection, where we have that this is governed by an incidence rate, so the amount of people meeting each other, let's say, with a parameter beta. And we have a recovery where infected people become recovered people with a recovery rate gamma. So we can actually draw up a simple model based on these differential equations. So the amount of susceptible people that gets reduced in time by this infection, the amount of infected, and those infected people get added to the amount of infected, to the I, which is the amount of infected people. And the amount of infected people here gets reduced by a recovery rate times the amount of infected, which then transition to a recovered class of people. So these are three equations, three first order ordinary differential equations with an independent variable of time. And we see that they are also nonlinear. So here we have this product S times I, which make these nonlinear equations. Now let's recast this into this form over here. And also note here that, well, y again is a vector as well as f. And we can do so by defining this vector y as follows, so that it holds that's a column vector which holds the function s of t, so the amount of susceptible people, the amount of infected people, and the amount of recovered people. Now we have to write what this function f is in terms of the components of y, and well, we can basically just take the derivative of y, which is the derivative of each of the components. We add or we fill in what these derivatives actually are. So the derivative of s is minus beta s times I. The derivative of I is beta si minus gamma I. And the derivative of r is gamma I. And then we can look at which components of y this corresponds to. So here now we have written out this system of three first-order equations as one vector equation that we can easily solve using any of the methods that we've seen so far. And in the next slide, I will give a brief demo on how to implement such a thing, such a system in MATLAB. So now I want to show you how straightforward it is to solve systems of ordinary differential equations when you already have solvers for single ODEs. Now, earlier in this lecture, we implemented the modified Euler algorithm and implicit Euler and explicit Euler. Now, well, we can choose either of these, but in this video I will use the modified Euler algorithm in order to solve the differential equations for an SIR model, in order to take a look at what happens in these epidemiological models. So I will write this up in a script such that I can easily change some parameters later. And I open up this file. So this is a script for simulating an SIR model as a demonstration for this course. Okay, so well, let's take a look at what this SIR model is. Well, let's briefly recall we have three equations. We have S for the susceptibles, and the evolution equation for S is minus this parameter beta times S times I. So that's kind of an infection from susceptible people to infected people. This amount of infected people gets added to the infection class. And from the infection class, well, we have a number of people that will recover, governed by this parameter gamma. And then finally, we have the amount of recovered people, and that is the evolution of that is governed by gamma times I. Okay, so we want to convert this into a system of ODEs. So we will convert this into a system where we have one vector solution which holds S, I, and R below each other. And then we want to find these equations that for dy dt is a function where f is a vector function of y. And we have to rewrite these things such that we have them in this form. And then once we have it in that way, well, we can use, well, our simple ODE solver, which we've used before. And these parameters are, well, we need to have a function here. So let's call this function f. And it needs some parameters. So the starting time, let's say that that's 0. The end time, let's parameterize this into t max. And let's also parameterize the time step and the initial condition. So we have to define these things, h and y0. Okay, let's just put some values in there. Let's say that we want to simulate for 100 time units, where that time units can be interpreted as days. Let's use a time step of 1/10 of a day, so that's about 3 hours. And let's make an initial condition. So this initial condition y0 consists of an initial condition for s. Let me make it as 0, an initial condition for I, and an initial condition for R, where these still have to be specified. Okay, let's normalize everything such that S0, I0, and R0 sum up to 1. And then instead of interpreting these as absolute amount of people, we can interpret them as fractions. So let's start out our simulation with no recovered people, with only a very small amount of infected people. So let's say that we take 1 in 1,000 people as infected. And well, in order to make this sum up to 1, we can then define the amount of susceptible people as 1 minus the amount of initially infected people. Okay, so far so good. Well, we have our initial time, the end time is defined, the time step is defined, and the initial condition is defined. Now what's left for us to do is to define this function f, which will be a vector function, such that we can incorporate these ordinary differential equations in there. And we want to use this ODE mod Euler function, and we will see that we have to do a very slight modification to this, but let's open this file up. So we see that this f, in order to work with this script, it has to be a function of the independent variable, which in our case is time, and the dependent variable, which in our case is the vector y. So let's write up this function, and for brevity I will just put it here. So we have the function and the output of this function, let's call this dy dt, is f of the independent variable t and the vector solution y. End. Okay, so now we have to start coding up this thing over here. Let me just copy it here. And we know that, well, the vector y holds these 3 solution components. So we can make this maybe slightly more explicit, saying that S is explicitly the first component of y, I is the second component of y, and R is the third component of y. We want the output here to be the derivative of y. So we need to find the derivative of s, so the ds dt, the dy dt, and the r dt, and then we just plug that back into this y vector, or dy dt vector to be more precise. The s dt, the I dt, and the r dt. Okay. All that's left for us to do is here, well, we need to define some parameters. So we need to define this incidence rate beta. Let's put this at a 0.25, for example, and a recovery rate gamma. Let's put this at 0.1 in this example. The only thing that's left for us to do in this function f here is to define the ODEs, so the right-hand sides of the differential equation. So ds dt, well, that's minus beta times s times I. Di dt, that's beta times s times I minus gamma times r, gamma times I. And the dr dt, well, that's gamma times I. Okay. So that should do it. This should be sufficient to evaluate the right-hand side of these equations, and we pop it back up into a vector such that we have a system of equations, and that is what is the output of this f function. Now this f function is then used by this ODE mod Euler in order to do the time integration, and let's take a look what will come out. Well, out will come the vector t for the time points where we have evaluated the solution, and the vector y, which will be the solution, so that will contain the amount of susceptibles, the amount of infected, and the amount of recovered in every time step. So let's see whether we can run this. Let me save it, give it a name. Let's call this demo SIR model. And let me dock this such that we have a bit more oversight. Okay, let's run. And we see that we encounter an error over here. And the error says that the index exceeds the number of array elements. Okay, so what we can then do is, well, we see that this error is in the ODE mod Euler file in line 16, where we try to evaluate f, and in this function, well, it seems that there is something wrong with the dimensions of y. So let's try to solve this problem by putting a breakpoint over there and running it again. And with this breakpoint, we see that we basically stop the code whenever we enter this space over here, this line over here. And we see that at this point, well, y is only a single value, so it's not a vector as we would suspect. So something is slightly going wrong when we're calling this f. Now this f is being called, let me clear this break, or let's leave it there for now. It's being called from the ODE mod Euler. So we need to probably do a modification here, and let me now save this as ODE mod Euler for systems. Okay, let's stop this in the time loop and run this again. Let's see whether, okay, this is ODE mod Euler system that we need, and we want to call not the ODE mod Euler, but the ODE mod Euler system function. And we put a breakpoint over there to see what happens, what goes wrong when we're calling this function f. Okay, let me run it now. And we see that indeed, well, the MATLAB engine has stopped at this line of the ODE mod Euler system file. And well, let's see what happens. So this xi, well, that's the time at the first time point, which is 0 indeed. And we see that here we have our y, which is indeed a vector, which holds the amount of susceptibles, the amount of infected, and the amount of recovered people. But we see that, well, this yi, it will only take one value out of here. So that's not really what we want, because, well, after we do some time stepping, this y will not be a vector only of time, but it will be a three-dimensional vector and also have a time dimension. So what we actually have to do here is that we have to take all rows of y and then the ith column of y. And this makes sense because y is not now simply a function of time, but it has three different functions of time. So we have to take every row here, and this should actually solve our problem. So let's quit debugging here. Let's remove these, breakpoints, and let's see whether it works now. Okay, so we see that by doing this very simple change to the time integrator, to this ODE mod Euler system, by this very simple change, we were able to, well, at least now we have a solution y that comes out of this, which is three-dimensional, so it holds the susceptibles, the infected, and the recovered, and in time it has 1001 time points. So obviously it makes more sense to plot this solution. So we know that the first row of y is the amount of susceptibles in time, the second row of y, that will be the amount of infected, and the third row of y, that is the amount of recovered. And let's plot this. So I'll draw this in a new figure. I'll draw everything together. So hold on, plot the time and the susceptibles, plot the time and the infected, and finally plot the time and the recovered. And we'll also add a legend: susceptible, infected, recovered. Okay, let's run it now. And we see that this is the solution to our system of ODEs from this initial condition where we have virtually only susceptible people with a very, very small seed of infection. We see that, well, the amount of infected people goes up, reaches a peak, and then goes down again. And after a while, more and more people recover, and the amount of susceptibles, well, more and more people get infected, and they also start decreasing. We can also take a look at what happens if we, for instance, change some of the parameters here. So if we double this incidence rate, which is kind of representative to how often people meet each other. So if there's less social distancing, then this beta could be, for instance, higher at 0.5. And if I then run the model, let's put these two next to each other. So this is for a beta of 0.5. This is for a beta of 0.25. So if beta increases, well, we see that this epidemic increases much more rapidly, reaches a much higher peak, but also is over faster. But so by reducing this beta, this incidence rate, we were able to flatten out this curve of infection. So with this video, I wanted to show you that it is, once you have a ODE integrator for a single ODE, extending this to systems is almost trivial.